before mini-lecturing on cosets, I wanted to give a brief mini-lecture on alternating groups, which was probably the trickiest bit from the adventure sheet on permutation groups. So the alternating group, AN, called the alternating group, consists of the subgroup of Sn consisting of even permutations. So what does it mean to be an even permutation? An even permutation is an element of Sn that can be written as an even number of transpositions. And remember, a transposition is just an element of Sn that switches only two elements. So for example, 1, 2 switches 1 and 2 in Sn, as long as n is at least 2. 4, 6. So this is 1, 2 in S6. 4, 6 in S6 is also an even permutation, or is also a transposition. And an even permutation is an element of Sn that can be written as a product of an even number of transpositions. So for example, the identity in any Sn can be written as either 0 permutations, where 0 is an even number, or 0 transpositions, where 0 is an even number, or it can be written as 1, 2, 1, 2, as long as we're working in S2 or bigger. So this is in Sn, where n is at least 2. So 1 is an even permutation. If I'm working in S3 or bigger, I could take 1, 2, 3, 2, 3 in S3, or S4, or S5, etc. And whatever this is must be an even permutation. I could write this out separately as a single cycle by writing, well, I don't know that it's a single cycle yet, but I could write this out as a product of disjoint cycles by first looking at what this product does to 1, which is here, nothing, and then here, 1 goes to 2. So I could write 1 goes to 2, and then I look at what this product does to 2, so 2 goes to 3, and then here nothing happens to 3, so 2 goes to 3, and then 3 goes to 2, and then 2 goes to 1, so 3 goes back to 1. So this product of 2 transpositions could also be written as 1, 2, 3, and this is even, which seems weird because it's a product of 3 because it's a 3 cycle. But it's even because it can be written as 2 transpositions. Likewise, something like 1, 2, 3, 4, oops, I shouldn't put an equal sign there, 3, 4, this is also even because it's a product of two cycles. This is my favorite way of writing this product because what does it do? It switches 3 and 4, it switches 1 and 2. There's not a way to write this as a single cycle. There's other ways of writing it. For example, I could write this as 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I like this way better, though. I don't know about you. So this is also even. However, the cycle 1, 2, 3, 4, which has 3 numbers, or 4 numbers, you might think should be even because there's 4 numbers here, but it can be written as a product 1, 2, 2, 3, 3, 4, which means that it's odd. And one of the parts on the adventure sheet from last time proves that a permutation can either be even or odd. It can't be both. And we use matrices to prove this. Ava and I did this exercise from the adventure sheet on permutation groups. So I'm not going to do this problem now, but I'll hint that if you translate permutations into matrices, you can use the determinant and the fact that a matrix only has one determinant to ensure that a permutation can only be written as an odd permutation or as an odd number of permutations or as an even number of permutations, but not both. So this idea or this notion of being an odd permutation versus an even permutation is a well-defined notion. And then AN consists of the even permutations. A question to think about is why if the set of odd permutations is also a subgroup.